Okay, so we're getting to the end of solving our equilibrium problems from initial conditions. We started off by solving a problem which has a perfect square in it, which is nice if we've got the nice square on the top and the bottom for all the terms. The last example we did, the situation develops where we cannot take that perfect square, but if the equilibrium constant is small, then that's all right. We can do a test for approximation, and if the approximation is valid, we can essentially force that x that's added or subtracted from the initial concentration, we can force it to 0. It's essentially so small it's not going to affect it. In this last example, you'll notice our equilibrium constant is quite large, 25, and we're going to result in a scenario where we cannot cancel out, we cannot have a perfect square, so we're going to have to actually go through the quadratic. As per normal, we will start with the ice table. 2Hi, H2, I2. They're all gases, so I don't include the gases. And the K, again, is 25. Normally, I write that down so that I can, in my mind, see whether it's, visually see whether it's small or large. In this case, fairly large, so we're worried, not likely going to deal with the approximation. 2 moles of H2 and 3 moles of I2 placed in a 1-liter vessel determine the equilibrium concentration of each gases. All right, this is an interesting example as well in that we're starting with we're starting with the product 3. So we're just following what it says. We don't have to get excited about it. 2 moles of H2 and 3 moles of I2 placed in a 1-liter vessel. So that's 0. There's our I. Now, in this case, like I said, you can't really screw it up which way you put the directions. And even here, you couldn't screw it up. But in this case, because it's all reactant, I think it makes good sense to put minus x, and plus 2x, because it's obviously going to have to shift left. There is no reactant molecule, so it's going to have to go that way. Even if you did it backwards, even if this was obvious and you put minus, plus, and plus, you would take the negative root. That would give you the correct answer. There's always going to be one root that gives you an absurd scenario, and you can always discount one of the roots. All right? And when I say absurd, it means that it results in a negative equilibrium concentration for something, and you can't have negative concentrations. In chemistry, a negative concentration is not a valid answer. I know in physics sometimes when you deal with the quadratic, you can get a negative time as one of your time roots. And that has meaning because if the quadratic was, continued back in negative time, that's where its position would be. But in chemistry, there is no, there is no way to evaluate a negative root, a negative concentration. All right, let's keep going then. 2x, 2.00 minus x, 3.00 minus x. All right, let's continue with the equilibrium expression. 25 equals 2.00 minus x, 3.00 minus x, and then that's over all of the 2x squared. Okay? Now, we actually encountered this equation before, and if the concentrations were the same, hey, we would have a nice perfect square, because if the concentrations were the same, I'd have 2 of the same terms up top, and it would be great. I could square it. We would take the square root, and away we would go. But as soon as those concentrations are different, they become different terms. Let's check for the approximation. It's kind of silly, but I just want to go through the motions. Taking that concentration, it doesn't matter which one. Usually we take the smallest one because that's going to give us the best evaluation of the approximation. Because I can have these terms up top. I'm going to take the initial concentration 2. I'm going to divide it by the K, 25, and we are definitely going to find out that that is not greater than 100. It's actually a decimal number of some sort. It's really tiny, right? Therefore, the approximation is no good. And therefore, we have to solve the quadratic. So at this point, what do? We evaluate our equation, and we put it into the standard form that we need in order to solve for the quadratic. We need an x squared term, we need an x term, a number term equals 0, and then put the numbers in and away we go. So at this point, welcome to math class. That's all we got to do. Get to the bottom of the question using math. So what am I going to do here? I'll bring this guy up top here, and that's going to be a 4x squared times 25. I did two moves there. I squared the 2 and squared the x and brought it up. And now I'm going to use distributive properties, because if I say FOIL, the math people get very upset. That's going to be out there on the internet. They really will be upset. And now I need some help from you. I don't do this stuff very often either. What do we got? 2 times 3. We got a 6. And then what do we have? Negative 2, negative 3. What's that? Minus 5. X. Let me know when I drop the ball. And then that's going to be plus x squared. Let me know when I make a mistake, because it can easily happen. I'm going to bring this in here. What's that? 100x squared. 100x squared equals 6.00 minus 5.00x plus x squared. My personal preference is to have a positive x squared term. That's just my personal preference of running through quadratics. So what I'll do is I'll move this positive 1x squared on the right over to the left, subtract it off, and get me a 99. I'll move everything else also to the left so that I can have that positive x squared term. So that's 99x squared, because I moved the other one to the left. And I'm going to bring everything else with it. My minus 5x will become plus 5.00x. And my positive 6 will become negative 6. And that's equal to 0. Again, let me know if I make any math errors, or hopefully you're ahead of me. So A is 99, B is 5, and C is negative 6. I'm going to go to the next page for this. A is 99, B is 5, and C is 6. And I know it's 6.00, and it's 100 to 2 significant digits. But for the sake of putting it into the quadratic, we can leave those off. We'll bring them back in at the end. Have I done anything wrong? Any concerns? We're okay? So here we go. Oh joy. X is equal to negative b plus or minus, what do we got? B squared minus 4ac over 2a. Negative 5 plus or minus b squared, that's 25, minus 4 times a is 99. What did I do? What did I do? Oh, good. Because I'm like, I got a negative under the root. That's the unacceptable thing. I love the quadratic. That's sarcasm, by the way. So this is negative 6 for all you out there on the internet. Negative 6. Woo! Negative 6 is making me feel better. Minus 2a, 2 times 99. I'm a fan of solving the root. So I got minus 5 plus or minus. I'll take the number for that whole root once you figure it out, over 2 times 99. What is 2 times 99? 198? 198. And I'll take the number just of the root. If someone could supply me with that, that would be great. You've got that root value? 2401. After the square root as well?
After the square root is 49.
Okay, I'll put another step. That's all right. Negative 5 plus or minus 49? 49 over 198. All right, let's get our two roots. So there's going to be a negative root, obviously, negative 5 minus 49 divided by 198, and then a positive root, negative 5 plus 49. So I'll take the roots. We got a root?
0.2.
That's my positive one, obviously. 0 point, sorry. 2, 2 repeating. 2, 2, and how many significant digits? 2. Excellent. And what's the other root? Negative 2.7. Can it be negative 2.7? It still can't be that big, can it? Can it be a 2? Really? Negative 0.27. That's okay. That's all right. Negative 0.27. All right. Beautiful. Now, putting it back into the equation, that negative root is going to get us absurd numbers for the final concentrations, right? So if we go back and take a look at our final concentrations, looking at the equilibrium concentration for H2, I stick a negative in there, and I'm going to get a negative concentration for HI, and you will always have one of the concentrations give you absurd negative concentrations. It may not be a negative number. It might be a number that, when subtracted, right, makes it is too big compared to what the concentration is. Like if my positive root was greater than 2, then that's going to give me a negative concentration. So one of the roots will give you a negative concentration somewhere. That is the incorrect one. And in this case, the negative root gives us the negative concentration. Therefore, no good. This results in negative concentration values. We can't use it. So let's go ahead then and solve the question, or answer the question. Does it ask for all concentrations? Yes. And I don't even remember what the equation was. Was it HI? I got to flip back. Yeah, it was so I'm looking for concentration of HI. Is that correct? What was that? Was that 2x? 2x? 2x. Does somebody have an answer for that as I'm babbling along here? Caitlin? 0.444 moles per liter. Concentration of, what's next? H2? Was H2 next? H2, and what was that? The 2 or the 3? 2.00 minus x, and I'll take an answer. 1.78. 1.78 moles per liter, and I2, that's the 3.00 minus x. That's got to be 2.78. Yeah, 2.78 moles per liter. All right? So, you either see a perfect square and you finish it, or you try for an approximation and you solve for it, and if that fails, you continue on and you solve for the quadratic. All right? We'll stop this business here.